In 1989, the Exxon Valdez oil spill in Prince William Sound devastated the unique ecosystem. Cleanup techniques further damaged the fragile system. Funding has been put aside to monitor the recovery of the system, and a major tool used by scientists in the Sound is a moored profiler that uses a variety of instruments to profile the water column twice a day. Unfortunately, the current system has a number of problems, so scientists at Prince William Sound turned to us to begin designing a new system. The biggest problems with the current system is that there is no remote charging capability. Scientists must go out and charge the profiler every month. Another problem is that there is limited data transmission. Much of the data is collected when the scientists are charging the system. And the profiler is proprietary and is no longer supported by the manufacturer. To overcome these challenges in the new system, we will implement a point absorber power generator to continuously charge the battery. We will include radio modules to remotely send data collected from the instruments and battery cells that will be received by a base station Raspberry Pi and shown on a user interface. Please meet our team that tackled this challenge. We are a group of 3 electrical engineers and 3 computer engineers. Today, first, we will go into specifics of the wave power generation device. Then we will talk about the data monitoring system. We will then show videos of the demonstrations, talk about a cost analysis, and make suggestions for future work. For our point absorber wave power generation device, the point absorber consists of 48 magnets meticulously arranged within a 3D printed holder enclosed, as seen in Figure 1, within a PVC pipe to maximize magnetic flux. To avoid the shifting of the 3D printed magnetic holder, we 3D printed solid cylinders that were inputted on both sides of the PVC pipe in order to hold the magnet holder in place in the center. Outside the PVC pipe, we designed a middle float that has over 7,000 coils winded inside of it to move up and down against the magnets from within the PVC pipe based on the ocean waves to generate power. In order to stop this middle float from exceeding magnet boundaries, we specifically placed stationary stoppers on each side of the PVC pipe to limit the range of motion of this float. There is a rectifying circuit between the wave power generator and the battery that allows for safe charging. The way it works is that the piezoelectric energy harvester is connected to 2 supercapacitors connected in series, which will store the power being supplied from the point absorber until they hit a certain threshold. Once that happens, the switch will close, allowing for the supercapacitors to discharge. This will then send power to the boost converter, then to the battery power management board, which will light up, verifying that the battery is being charged. Next, we have an overview of the communicating components on the prototype moored profiler and the base station. On the top in the orange box are all the subcomponents on the prototype profiler. On the left, we have the battery management boards, which monitor the voltage and temperature of the batteries and report it to the Raspberry Pi. Under that, we have an example instrument, a digital compass, that collects various readings and sends them to the Raspberry Pi. Next, we have a winch that the Raspberry Pi commands to raise and lower the profiler. Finally, when the profiler is at the surface, the LoRa radio transmits data from the battery management system and compass back to the base station. When the base station receives data, the Raspberry Pi parses the data, stores it in TXT files, and displays it in graphs on the user interface.
So first we're going to test the generator, assuming that the waves are really slow. I'm going to hit single capture on the oscilloscope. The output is about 3.5 volts. Now we're going to assume that the waves are a little faster. The output here is about 8.78 volts. This is our charging circuit. This is where you get the input from the generator. Just to test the circuit, we won't be hooking up the generator. We're going to provide a constant source of 6.10 volts to the circuit. And we're currently waiting for the caps to charge up, which is what we're monitoring right here. Once the caps hit about 3.6, they start discharging. The circuit is then closed, and as you can see, the red light is on, which indicates that the battery is in fact charging.
In this demonstration, we show the data monitoring system. It first reads data from the digital compass and battery management system. Then, the winch deploys as shown by the motor on the left. This would send the profiler to the surface. Once it reaches the surface, the radio sends the data out and the base station receives it, saves it, and displays it on the user interface shown on the right. This updates as more data is received. The winch then rewinds, bringing the profiler back underwater to collect more data. It then restarts this loop by collecting data again.
So this is how our system works all together. We have a generator which generates power, sends it through the circuit, and the circuit charges the battery. As you can see, the red light is on, so that means the battery is charging. The battery powers the rest of the system, and we use this to monitor the battery.
With a total budget of $700, we only spent $311.89 on our system. Here you can see the breakdown of the cost. The biggest costs were the magnets for the generator device and the communication radios. However, many items used in the prototype were provided by the labs at Georgia Tech and were not considered in the final cost. There is a lot of future work to be done to get the system ready for the scientists at Prince William Sound. Some of this work includes scaling up the small, unit-scaled version of the power generation device to implement in the real version, to test the prototype in the real environment, to add additional software error checking, to add antennas to the radio that allows communication for up to 20 kilometers, and to implement the mechanics of the winch. Thank you so much for watching our presentation.